Okay, so one of the things I want to emphasize is that with with any problem, right? When we're talking about hardness, we're going to limit ourselves to simply talk about decision problems. And that's important because in the first part of the course, we talked about how we reduce any problem into a set of strings, right? So basically, we had oh, I know. Let's say the addition of the addition of two numbers, right? This is the problem, right? And we simply define a set I'll add 2 that's simply 1 plus 1 is equal to 2, a string like that. Um, 2 plus 1 is equal to 3. Uh, 1 plus 2 is equal to 3, dot, 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 dot. Okay? We limited ourselves to all the sets of strings, right? And then we said that a machine is able to do that problem, to answer that problem, if it's able to recognize whether or not a particular string is part of the language of that problem or not, right? So this standardization made it possible for us to answer the question of what machines are capable of answering which problems. How powerful does a machine need to be in order to perform addition? How powerful does that machine need to be in order to perform multiplication or finding a path in a graph, right? So so that's how we standardize problems in computational complexity. That all problems are sets of strings. Here, we're not so restricted, right? We're not so restricted to defining problems as sets of strings. However, we have to define the problem output, right? We have to have some commonality for the problem. We have to have some A to A comparison. And the most intuitive thing to do when we're talking about hardness of a particular problem is simply to say the output of the problem has to always be a yes or no answer. Okay, so for any given instance of a problem, the output has to always be yes or no. And if we formulate every problem that way, then that allows us to compare problems to each other. So, what would that look like? Well, let's say, I'm going to come back to that slide in a minute, but let's say we have the traveling salesman problem. Okay, so I'm a computer engineer, and when I first learned the computer traveling salesman problem, I heard the common formulation that you're given a list of cities and the distances between each pairs of cities, and then you wanted to take a route that visits each city exactly once and returns to the origin city, right? You wanted to take the shortest route that visits all the cities, right? The salesman wants to save gas, but he still wants to get to all the cities. Okay? Now, the output of that formulation is a path, right? And it's pretty hard for us to compare that problem or to do any reductions for that problem to, I don't know, the halting problem, right? It does a program. It will, if you run a program, will it stop on input W? We don't know that. Like they're just two different things, apples and oranges. Instead, what we do is we reformulate the problem as a decision problem. For instance, given a list of cities and distances between each pairs of cities, is there a route that visits each city exactly once and returns to the origin city while having a length shorter than k? Okay, that little addition, instead of saying what is the shortest path that visits all the cities, you say is the length shorter than k, then some constant. That allows us to have a new formulation of the problem that outputs yes or no. And then we could talk about the hardness of this problem. Okay? Now this problem actually is considerably easier than this problem. Okay? This problem is in non-deterministic polynomial time. This problem is in, it's not in NP. It would be in exponential time, I believe. okay? Because this is an optimization problem. And even a non-deterministic machine would have to compare the quote-unquote output given by a machine that answers this problem against all possible paths, all possible salesman's paths, to ensure that the output is shortest, right? In this case, a non-deterministic machine could very easily verify that there is a path shorter to k by simply looking at the path and making sure that it doesn't cost more than k. Okay, and if you're unsure of what that means, we're going to talk more about it later in a lecture and in the next lecture. But the major point is that in order to compare problems together, we need to reformulate them as decision problems. Okay. And also, just one quick thing about encoding is that we are going to use the angle brackets to denote encoding. Okay, so similar to when we talked about universal Turing machines, we said that there is a machine M, and then there is the encoding of that machine that you could feed into another Turing machine, right? Every machine M can be encoded as a particular string. So, same thing here. N is an integer in this case, and angle brackets n is the encoding of that integer in some format, probably binary. G is a graph, and the brackets graph is the encoding of that graph in some format. Okay. And M is a Turing machine, and the angle brackets M is the encoding of that Turing machine. So that's what that means. That's what the angle brackets means. So we're going to have to talk a lot about the difference between the actual object and the encoding of that object, as we did when we talked about complexity, computability in the first part of the course. Okay.